In this video presentation, I'll be talking about applying the Chatelier's principle in the topic of chemical equilibrium. Before we talk about factors affecting the equilibrium, let's first talk about what Le Chatelier's principle states. Le Chatelier's principle states that if a system is in dynamic equilibrium and it is subjected to a change which disturbs the equilibrium, the system will respond in such a way to counteract the effect of the change. Hence, the following are factors that will affect equilibrium. Firstly, concentration, pressure, and that only happens when there is a change in number of gas particles, as well as temperature. Temperature will only affect equilibrium if and only if that the reaction's enthalpy change isn't equals to 0. Factors that do not affect equilibrium are as follows. Firstly, addition of a noble gas. Although there is a change in total pressure, but there is no change in the partial pressure of the constituent gas in the equilibrium. Catalyst. What happens here is the catalyst will not affect the equilibrium position, but it will cause the equilibrium to be obtained earlier. So first and foremost, let's talk about changes in concentration. I'll be using Haber process as our example to illustrate how changes in concentration affect the equilibrium. Using the kinetics to explain, firstly, when hydrogen is added, the rate of the forward reaction will increase. The equilibrium position will therefore shift to the right, and hydrogen with nitrogen will combine to form more ammonia. Using Le Chatelier's principle to explain this effect, first and foremost, when hydrogen is added, the equilibrium will respond to counteract the effect of the disturbance. The disturbance is the hydrogen that is being added. The equilibrium position will shift to the right, the forward reaction is hence favored, and therefore more ammonia is formed. Now, do note that the concentration of hydrogen at the new equilibrium is actually still greater than the concentration of hydrogen at the initial equilibrium. This goes to show that the equilibrium will respond to counteract the effect of the disturbance. It does not remove the effect of the disturbance totally. If we use a concentration time graph, we are able to track changes in concentration and see how it affects the equilibrium. Initially, hydrogen actually decreases until it reaches constant. The concentration of ammonia increases until it reaches constant. At this portion, this is where we've reached and obtained our first equilibrium. At time t, we have decided to add more hydrogen. What happened here is, by Le Chatelier's principle, the equilibrium position will now shift to the right, causing the forward reaction to be favored. Hence, we would see that the concentration of hydrogen decreases, whereas the concentration of ammonia increases. At this point, when at the constants, we would see a new equilibrium being achieved. Do note that the difference between the hydrogen concentration at the new equilibrium is actually greater than the concentration of the hydrogen at the initial equilibrium. So, what happens if ammonia is removed at a constant volume? By Le Chatelier's principle, the equilibrium will respond to counteract this effect. So what happens will be the equilibrium position will shift to the right. The forward reaction will be favored. Nitrogen and hydrogen gas will react with each other, causing the yield of ammonia to increase. However, if you continue to remove ammonia, this will cause the reaction to become complete because it is not possible for the backward reaction to take place. In this portion, I'll be talking about the effect of pressure. I'll be using the Haber process once again to discuss how pressure will affect the equilibrium. Pressure changes only affect equilibrium with gas particles. The equilibrium reaction must have a change in number of gas particles. That's because the number of gas particles is proportional to the pressure. The effect of pressure can be caused by pressure changes or volume changes. When volume decreases, pressure would increase. This will cause the equilibrium will shift in a manner to try to decrease the pressure. The equilibrium position will shift to the right, with the forward reaction being favored because fewer gas particles are being formed. More hydrogen and nitrogen gas will react with each other to form more ammonia. In this graph, we will use a concentration time graph to show how effect of pressure will affect the equilibrium position. The concentration of hydrogen will decrease until it reaches a constant. The concentration of ammonia will increase until it reaches a constant. At this period, we have obtained our first equilibrium. At time t, when pressure increases, what happens here is that the concentration of hydrogen and concentration of ammonia will increase because the volume that the gas exists in decreases. By Le Chatelier's principle, the equilibrium position will shift to the right, causing a decrease in concentration of hydrogen. While by Le Chatelier's principle, the concentration of ammonia will increase. This happens because the forward reaction reduces the number of gas particles in the equilibrium. At this point, we will have obtained the new equilibrium. What you notice is that the rate of the equilibrium is reached is faster. The number of hydrogen gas decreases and the number of ammonia increases. Do note that it is not necessary that the concentration of hydrogen is definitely going to be smaller than the concentration of ammonia. We will use the following example to showcase how LCP can be applied when pressure increases. An increase in pressure will result in the position of equilibrium to shift to the left. That's because the number of gas particles in the backward reaction is smaller than the forward reaction. A decrease in pressure will result in the position of equilibrium to shift to the right. That's because the forward reaction increases the number of gas particles as compared to the backward reaction. In this equilibrium, in this reaction, there is same in the number of moles of gas when the reactants form the product. Hence, the changes of pressure have no effect on the position of the equilibrium. Now, using this equation, we are talking about Haber process again to talk about effect of pressure. This time round, I'll use a simplified equation where it shows that this reaction is an exothermic reaction because energy is being produced from the reaction. Using Le Chatelier's principle, when temperature decreases, the equilibrium will respond to try to increase the temperature. The equilibrium position will shift to the right and the forward reaction is favored because it is exothermic. More ammonia will be produced and therefore our Kc or our Kp, the equilibrium constants, will increase. Using kinetics, we can also explain the effect of temperature. What happens here is when temperature decreases, both the rate of the forward and the rate of the backward reactions will both decrease. The activation energy of the backward reaction is actually larger for an exothermic reaction. Hence, you would expect rate of the backward reaction to slow down more than the forward. As a result, the forward reaction was favored, the equilibrium position will shift to the right, and the equilibrium constant will therefore increase. Now, we will use the energy profile diagram to help us to explain the kinetic aspects of explaining the decrease in temperature. As mentioned earlier, when temperature decreases, the rate of the forward and the backward reaction will decrease. The activation energy of the backward reaction is larger for an exothermic reaction. As you could see, the forward activation energy is labeled in green. The backwards activation energy is labeled in red. You could see that the activation energy of the forward reaction is smaller than the activation energy of the backward reaction. As a result, when you decrease temperature, the rate of the backward reaction will slow down more than the forward reaction. As you can tell now, forward reaction will therefore be favored. Our equilibrium position will shift to the right. As you could remember, the equilibrium constant is actually the ratio of the rate constant of the forward reaction to the rate constant of the backward reaction. When we decrease in temperature, both forward and backward reaction will decrease, but the forward reaction will decrease less than the backward reaction. As a result, the rate constant of the forward reaction will decrease in a smaller amount as compared to the rate constant of the backward reaction. This will result in the equilibrium constant to increase. We'll be using this example to explain how increased temperature will cause the equilibrium position to be affected. We'll be still using the Haber process as our example. Using Le Chatelier's principle, you can observe that when temperature increases, the equilibrium will respond to try to decrease this temperature. The equilibrium position will shift to the left. The backward reaction is favored because it is endothermic. Less ammonia will be produced. The equilibrium constant will decrease. Using kinetics to explain, what happened here is when temperature increases, both the rate of the forward reaction and the rate of the backward reaction will increase. The activation energy of the backward reaction is larger, hence you would expect that the backward reaction will increase more than the forward reaction. As a result, the backward reaction will be favored, the equilibrium position will now shift to the left, and the equilibrium constant will therefore decrease. Now, using the concentration time graph, we can help ourselves to see how temperature increases will affect the equilibrium position. Concentration of hydrogen gas will actually decrease until it reaches a constant. Concentration of ammonia will increase until it reaches a constant. At this point, we have obtained our first equilibrium. At time t, what happened here is we have increased our temperature. And when you increase in temperature, the equilibrium position will now shift to the left and the backward reaction is favored. So you could see that the concentration of hydrogen increases and the concentration of ammonia actually decreases. At this point, we have obtained our new equilibrium. Do take note that because our temperature has increased, you could see that the rate in which the equilibrium is reached is faster. And this can be denoted by the curved area of the green lines. Using this, we will explain how the effect of catalyst is on the equilibrium position. When a catalyst is added, both the rate of the forward reaction and the rate of the backward reaction increases by the same extent. We observe there is no shift in the equilibrium position. However, the rate in which the equilibrium is achieved is faster. That is the end of the video presentation for the effect of Le Chatelier's principle in chemical equilibrium.